Okay, so we've talked about how to take a vector when we've been given its magnitude and direction and use that information to figure out its components. In some sense, what we want to do now is go in the opposite direction. So if we know the components of a vector, how can we use that information to get magnitude and direction? And so just to set this up, I want to come back to thinking about what we know about right triangles from our review of trigonometry. And we said there are really sort of four kind of powerful tools that we can use with right triangles. There's the Pythagorean theorem, cosine, sine, tangent. Pythagorean theorem, in terms of the way that we've set this up, is going to relate the sides of our right triangle. So A and B are the legs, C is the hypotenuse, and the Pythagorean theorem tells us how those three things relate to each other. The tangent, well, once we've picked an angle theta, now I can talk about the adjacent and opposite legs. And so in our picture here, A is adjacent to theta, B is opposite to theta, and tangent's going to relate the length of A, the length of B, and the angle theta. Cosine, again, is going to relate the adjacent side, the length of the adjacent leg A, and the hypotenuse C. So AC and theta get related in the cosine, and then sine relates the opposite side, the hypotenuse and theta. So BC and theta. So we've got four really powerful tools. And again, what we've done so far is say that so if I have a vector C that happens to point out here in a certain direction, it makes an angle theta with the x-axis, then I can figure out, so what I'm interested in is basically thinking about how that information that I had previously now maps to talking about the vectors. Well, the hypotenuse, the length of the hypotenuse is going to be equal to the magnitude of the vector C. Theta is still going to be theta, that's telling me the direction, so we'll talk about that angle as giving us the direction of the vector. And then my legs A and B are going to be the lengths of those components. So the legs A and B will tell me what's going on with the components Cx and Cy. So the x and y components of vector C now sort of map to the legs. And so previously what we've done is said, well, if you know the magnitude and direction and you want to get the components, we're going to use cosine and sine depending on where that angle theta is defined. So if your angle theta is defined relative to the x-axis, then you're going to use cosine theta to get the x component. If your angle theta is defined relative to the x-axis, you use sine theta to get the y component. If you define theta relative to the y-axis, those two trig functions flip in terms of which one you use in either the x or y component. But we want to go in the opposite direction here. So now we want to say that we know what the components are. So I know Cx and Cy, but what I'm interested in is the magnitude and direction. I want to use the Pythagorean theorem and the tangent. And what we'll see is the Pythagorean theorem, we're going to go ahead and a squared plus b squared equals c squared. We're going to go ahead and solve that for c, and so we'll end up talking about something that has the square root already taken care of in it. And then again, tangent, we're basically going to recognize that, well, to get theta, we want to take the inverse tangent. And so that's the way that we'll end up dealing with getting the magnitude and direction. So again, let's come back to our example here. So I've got the vector c. I know that its x component is 16.4 meters pointing in positive x. Its y component is 11.5 meters pointing in positive y. If what I want is the magnitude, the phrase we're going to use to describe this is just simple shorthand, is we're going to call this Pythagorizing. So we're going to say that, well, we Pythagorize to get the magnitude, so we're going to take the square root of the x component squared plus the y component squared. Okay. In this case, 16.4 meters squared plus 11.5 meters squared, take the square root of that, you happen to get 20 meters, which is the magnitude of vector c. If I want the direction of vector c, then I'm going to use the inverse tangent. So again, theta, in this case what I've defined to be theta, is going to be equal to the inverse tangent of, and notice I'm using the y component over the x component. We'll come back and talk more about this in a second. And so when I plug this in, this tells me that theta is going to be the inverse tangent of 11.5 divided by 16.4. My calculator tells me that's 35 degrees. The detail that we want to add here is that 35 degrees, we want more information. So when we're reporting the direction of an angle, knowing that the angle of theta is 35 degrees is good, it's not necessarily enough. So we need some more information here to correctly report this angle theta. So what's this additional information that we need? Well, really what you want to give, if you want to correctly report an angle, is three particular pieces of information. How far you rotate, in which direction you rotate, and where you need to start rotating from. So in this case, how far you rotate, that's the 35 degrees. In which direction do you rotate? Well, that's again related to where I'm starting to rotate from. But the one thing that we'll point out is, so if you think about starting at the positive x-axis and you rotate towards positive y, that's defined as a positive rotation. If, on the other hand, you start at the positive x-axis and rotate towards negative y, those are negative rotations. And so in this case, what I'm going to do is I'm going to say that when I calculate my angle theta, notice that I have put the x component on the bottom. That x component being on the bottom tells me that I want to start rotating from the x-axis. And so in this case, I'm going to rotate 35 degrees from the positive x-axis in the positive direction. So one way that I can report this is I've rotated positive 35 degrees from the positive x-axis. Another way that I can say it is that, well, that's 35 degrees above the positive x-axis. Okay? Sort of above is taking care of the plus or minus in terms of the direction of rotation. Let's take a slightly more complicated example here. So again, vector D here has an x component that's negative 4.2 meters and a y component that's negative 9.1 meters. Okay, so I can draw that out. Obviously, the x component is going to point to the left. The y component is going to point down, given the axis I have here that says positive x points to the right and positive y points up. To get the magnitude of vector D, again, that's straightforward. I'm going to Pythagorize. So x component squared plus y component squared, take the square root, so negative 4.2 meters squared plus negative 9.1 meters squared, take the square root of that, I get 10 meters. One of the things to point out, because it's easier to make mistakes if you and your calculator disagree about what's going on here, notice that when I Pythagorize, my answer should always be larger than the two components that I'm plugging in. So if you don't take care of your minus signs correctly and plugging it into your calculator, you could get a number that doesn't make sense because it says that your magnitude of your vector is actually less than one of your components. So that's something simple to always check. To get the direction, so I've labeled the angle here phi. To get the angle phi, again, I'm going to use the inverse tangent. I've picked the inverse tangent of y component over x component. When I plug that in, it's the inverse tangent of negative 9.1 over negative 4.2, and my calculator gives me an answer that says plus 65. So now I need to figure out what that means. Well, the plus 65 we'll deal with in a second. I know because I put the x component in the bottom of my ratio inside the inverse tangent that I'm defining my angle from the x-axis, somewhere along the x-axis. And because my x component is negative, that tells me that the angle my calculator is giving me is actually defined from the negative x-axis. So I care about two things here. One is relative to what axis. That's going to be just what component did you put in the bottom of your ratio for the inverse tangent. The second is, well, what's the sign of that component? Because the sign of that component is which side of that axis you actually need to start from. So I'm starting from the negative x-axis, and again, I need to go in the positive directions, what my calculator is telling me. I just want to check and make sure that that makes sense, and sure enough, if I think about rotating in the positive direction, that means I'm rotating, in this case, from positive x towards positive y, and if I keep on going, If I start from negative x and go 65 degrees, sure enough, that gets me the correct direction for vector d. Again, I can also, instead of worrying about the plus or minus for the 65 degrees, I can simply say that this is 65 degrees below the negative x-axis. Gets me the same answer. So what we want to be very, very comfortable with is going in either of these directions. If you're given the magnitude and direction of a vector, you want to use cosine and sine to get the components. If you're given the components of a vector, you want to be equally comfortable in either Pythagorizing or using the inverse tangent to get the magnitude and direction of the vector. And you should be able to do this in either direction equally comfortable, because we're going to have to do this all semester long in dealing with vectors.